স্ক্রিন দেখা যাচ্ছে?
হ্যাঁ ম্যাম।
Okay, we will discuss separation of loss of DC machine today. Now, objective of the experiment to separate the different losses of a DC shunt machine. Now, actually what happens for electrical machines, there will be different types of losses, and these losses manifest itself as heat, and also that affects the efficiency of the machine. Now, when we are operating a machine, actually it is customary that the user should know its approximate expected efficiency, temperature rise, and other performance when it is operating, because before put into service, this information should be available with the user so that they can select a proper machine. Now, first of all, for large machines, it is not practicable to run the machine with full load and then measure its losses. And even in that case, you can measure the total loss. To separate it out is not possible. So there are different test methods by which we can separate and the losses of different types of machines. For all rotating machines, there are different tests. Now, for DC machine also, we have different that this is one of the tests. It is not the only one. There are other tests also, but this has been selected. This is a very simple method and very easily can be easily carried out in the laboratory. Now, so our objective is to separate the losses of a DC shunt generator. Now, what are the losses of a DC shunt generator when it is running? First is the armature copper loss. Current is flowing through the armature winding made up of copper. So there will be I square loss in the armature. Then there will be field copper loss. Field winding, the current is flowing. So there will be I square loss in the field. Then there will be core loss. Now, actually core loss has two parts, eddy current and hysteresis loss, which is inherent with the alternating magnetic circuit. In case of DC machine, you know, you have studied DC machine, though we have DC excitation, but actually there will be eddy current and hysteresis loss in the armature because the flux linkage of the armature is changing due to the motion of the armature with respect to the fixed flux. So there will be core losses. So there will be windage and bearing friction loss and brush friction loss. Windage loss is basically the machine is rotating in wind because our atmosphere is filled up with wind, and this wind opposes the motion, and so there will be losses. So that is the windage loss. And bearing friction loss is basically due to the friction of the bearing with when the shaft is rotating, there will be losses. And there will additionally, as DC machine, we have brushes, so there will be brush friction loss. There is friction between the brush and the commutator surface, so there will be loss. Now, in general, the losses in any rotating machine can be broadly classified into broadly due to three categories. One is the losses due to changing magnetization. That is, if the flux is changing, there will be losses. This loss is basically there will be hysteresis loss and eddy current loss in the core due to this changing magnetization. Then losses in the electric circuit. This is basically I square loss in the windings, and there are mechanical losses. So the previously I have shown the losses in DC machines. So this armature copper loss and field copper loss is associated with the electric circuit. This core loss is associated with alternating magnetization, windage and bearing friction loss, brush friction loss. This will be due to these are mechanical losses. So in this is a losses in a rotating machine. Loss due to tangenting magnetization is the iron loss or the core loss. Loss in these are the hysteresis loss and eddy current loss. So losses in the electric circuits includes for armature winding loss, series field winding loss, interpolar winding loss, compensating winding loss, brush contact loss, then this shunt field winding loss. Mechanical losses include brush friction loss, windage loss, bearing friction loss. So these losses we have to separate. Now the losses can be classified as these losses can be classified as constant loss, losses which vary directly proportional to the load current, and losses which vary in direct proportional to the square of the load current. For DC machine, this constant loss is obviously the core loss. Then losses with direct proportional to the load current is here the brush friction loss. That is the brush contact loss because due to the brush contact resistance there will be I square loss. That is the brush contact loss. Losses with directly proportional to the square of the load current is the I square loss. So constant loss are these I have told the constant loss and the core loss only. Besides that, the other few losses you can keep that constant loss if the speed is constant, like the bearing friction loss, brush friction loss. These are constant if the speed is constant. Basically, these losses are speed dependent, not dependent on voltage or the current of the machine. Then the field copper loss can be I am discussing in the point of view of a DC shunt machine. So the different losses we have in a shunt machine, that are what we have discussed is the armature copper loss, the field copper loss, then the core loss, brush friction loss, windage loss, and the bearing friction loss. Now these losses can be broadly classified into three categories. So one is the constant loss. Now the constant loss, we can consider the bearing friction loss and brush friction loss is constant for a particular speed. If the speed varies, this loss will vary. Then the field copper loss is obviously we know this is I square loss of the field, I square R loss, but the field copper loss will be constant if we keep the field current constant, because it's a shunt machine, so we can keep the field current constant. So if we keep the field current constant, then the field copper loss is constant, and the iron losses, which includes the hysteresis and eddy current losses, those we know depends on the frequency and the flux density. So if we keep the field current constant, then the flux density will be constant. Then these losses will be, if the speed is constant, these losses will be constant. So iron losses are constant for a constant field current and constant for a particular speed. So losses proportional. So from here we can see that for a particular speed, bearing friction loss, brush friction loss, iron loss, and the field copper loss, these total losses can be treated as constant loss. Now losses proportional to the armature current. Losses proportional to the armature current is the brush contact loss. So losses proportional to the square of the armature current are copper losses in the armature winding, interpolar winding, and compensating winding. Interpolar and compensating winding, you know, it are in series with the armature winding. So this is a small machine, so we do not have those compensating winding and others. So various losses will result in temperature rise of the machine. When the motor or generator is running, its temperature will tend to rise above that of the ambient. Now, initially, temperature rise steadily, then at a point is reached when the heat dissipated from the machine is at the same rate as it is produced inside the machine, then the temperature becomes steady. Normally, for any normal design machine, it takes almost around 2 hours to stabilize the temperature. Now, we can be expressed the losses in this form, that is the total loss having three components. One is the constant loss, one is proportional to the armature current, and the third component is proportional to the square of the armature current. So the efficiency will be, it is DC machine, so efficiency is V into I minus the losses divided by Vi. So can be written as 1 minus A plus Bi plus Ci squared by Vi. So equal to 1 minus A by I plus B plus Ci, where this capital A, B, C are given by small a by V, small b by B, and small c by V. So now this is our circuit diagram. So basically what we have two DC machines coupled together. One will act as a motor and other will act as a generator. We will separate the losses of this machine, which is operating at generator. So this machine which is connected as motor is a shunt motor, so connected through a open starter. So there is a resistance in the armature circuit, there is a resistance in the field circuit. We have ammeter in the armature and field circuit. Now, varying these two resistances in the armature and field circuit, the DC machine speed can be varied. DC motor speed can be varied. Now, and for the generator, it will run at no load. So we have only the voltmeter at the terminal, and it is separately excited. So this is the circuit for field excitation. We have the resistors connected as a rheostat, so that we can have broad variation of the field. Now, what happens? Just think that if we decouple the machine and run only the shunt motor, then what are this motor is running at no load. So what are the losses? The losses is supplied from the DC supply here. So the losses of the motor will include windage and bearing friction loss of the motor, brush friction loss of the motor, armature I square loss of the motor, field I square loss of the motor, brush contact loss of the motor. So it will, as motor is running under no load condition, so the supply is supplying the losses of the motor under no load. Now, amongst these losses, we have seen that this brush contact loss is very small, that we are not considering separately. So what losses we have is the losses in the field, the core loss, the friction losses, different friction losses, and I square loss. Now, this I square loss depends on current. So if we take the total input from here, that is V into I, and that minus I square R, we measure the resistance of the armature. So the minus I square R will give you the other losses. Other losses include the bearing friction loss, windage loss, brush friction loss, field copper loss, and the iron loss. Now we have seen that these losses are constant if we keep the field current constant and the speed constant. So what we do, keeping the field current field current of the motor constant, you can keep the field current constant by this rheostat. So keeping the field current constant, we run the motor at different speed. It's from low to creeping speed to the rated speed in the steps of 100 rpm. So for different speed we can change by, because we are going below the base speed, so it will be obtained by changing the resistance in the armature circuit. So we will record the voltmeter and ammeter reading for different speed, and for each reading from Vi minus I square R loss, we will get motor constant loss for that particular speed. Now this generator is coupled with the motor, and say we lift the brushes are not there. Then again we run the motor for the same, the field current should be same. For the same field current, we run the motor at vary its speed over the same range. Thing should be noted that for each and every set, the various speed should be constant. That is, say for initial one, that when the motor is uncoupled, so we have taken reading for say 100 rpm, 200, 300, 400, 500, etc. Then for all the subsequent runs, we should have readings for the same speed, because unless we keep the speed concept same, we cannot separate out the motor losses. If we keep the speed constant, then the motor portion of the loss can be subtracted as a motor constant loss. And the I square loss we can take care of by the current and the resistance. So under this condition, when the generator is coupled, the brushes are lifted. So under this condition, what are the losses? There will be losses corresponding to the motor, all the losses what we have discussed. Additionally, for the generator, we will have windage and bearing friction loss, because it is rotating. Windage and bearing friction loss will be there as it is rotating. So from the for this reading, so we for each and every speed we calculate Vi, that is the input, minus I square R of the motor, so and get the losses. So that loss will include the motor constant loss and generator windage and bearing friction loss. So we have calculated the motor constant loss in the previous run, so that if we subtract from this loss, we will get the generator windage and bearing friction loss. Now we replace the brushes in the brush holder and again run the machine for same set of speed and note the same readings. So under this condition, what will be the losses? There will be all losses associated with the motor. For the generator, there will be windage and bearing friction loss, and additionally there will be brush friction loss. So for this run, again we calculate the losses, that is the Vi, that is the input, minus I square R of the motor will give us the motor constant loss, plus generator windage and bearing friction loss, plus the brush friction loss. So from this run, by subtracting the windage bearing friction and constant losses found in the previous run, we can get the brush friction loss of the generator. Now we give excitation to the field circuit. So field circuit, normally corresponding to the full rated voltage at rated, so that the rated voltage is obtainable at rated speed. Now, keeping the field current constant at that value, we again note the same readings. So VI input here minus I square R of the motor will now give us all the losses of the motor plus windage and bearing friction loss of the generator, brush friction loss of the generator, plus the core loss of the generator. So we can from this run, by subtracting the other losses already calculated, we can separate out the core losses. So the DC machines ratings what are used in this experiment are DC motor, 3-phase, 115 volt DC, 23.7 ampere, 1150 RPM. Field current, this is the rated speed. Field current is 0.935 ampere. And the generator for which we are separating the losses is 2 kilowatt, 125 volt, 16 ampere, 1150 RPM. This is the compound winding. So we have a 4-point starter to start the motor. And the meters we require will be the voltmeter 0 to 150 volt, numbers, one for measuring the motor voltage and the one for the generator voltage. And this one 0 to 30 volt, this is required for measuring the resistance, armature resistance. Then we have the ammeter. Ammeter are 0 to 2.5 by 5 ampere, two numbers, one in the field actually this will be actually three numbers, because one in the field of the motor, one in the armature of the motor, and one in the field of the generator. And this 0 to 20 ampere ammeter, this is required for the resistance measurement. Then we have the load box. This is required for again resistance measurement. Then we have the tachometer, and we have the rheostat in the field circuit of the motor and the generator. So first run is that run the set for half an hour to stabilize the temperature. Now actually to get the total, to make the temperature totally stable might take longer, but if we run for half an hour, more or less the temperature will be near to the stable value, because the resistances you know are related to temperature. So whenever we carry out any measurement on any particular machine, rotating machine, we have to run for half an hour, or preferably more than that, so that the temperature is stable. Now for the run 2, this is the first run I developed I described was the motor was uncoupled, but normally that is carried out at the end, because we have to uncouple the motor and generator. So we started from generator brushes taken off. So we keep the speeds, it is 100, 200, 300, 400, 500 up to 1200, because 1150 is the rated. We note the motor armature current, motor terminal voltage, and motor field current is kept constant. So from here, we will get this is the input. Motor terminal voltage into current is the input. The resistance we will measure at the end. So VI minus I square R of the motor will give you the windage and bearing friction loss of the generator. Then this run, the generator is unexcited. That means we have replaced the brushes. So we will again, if you note the readings, that we have replaced the brushes, so brush friction loss is added. So if you get this into this is less than this input here, because brush friction loss is added. So here we note the readings are the same. That is, we note the speed for the same set of speed. We note the motor armature current, motor terminal voltage, and the motor field current keeping constant. So this V into I minus I square R loss of the motor will give you the generator windage and bearing friction loss and the brush friction loss. So between the this run and the previous run, we will get the brush friction loss. So note one thing, that if you are asked to find out the, say, the brush friction loss only, then there is no need to perform all the runs what we have I have described. If you perform this run and the previous one, then the difference between these two will give you the brush friction loss. Now, next one is the generator excited. So here additional is the generator field current is noted. Both the field current are constant, because unless the field current we keep constant, the flux will vary. And with the speed, you can see the voltage is varying, generator voltage is varying. So here this V into I has increased further because the core loss is added. So this is VI, this V and this I, minus I square R of the motor, I square R loss will give you the generator core loss plus the brush friction loss plus the windage and bearing friction loss. So difference between this run and the previous run, that is run 4 and run 3, will give you the core loss. Now this one is the motor uncoupled. So here it is V into I minus I square R will give you the motor constant loss for a particular speed, obviously, and for constant field current. So note that the motor field current is constant for all the runs. Now we have to measure the armature resistance also. So both for the motor and the generator. For the motor, it is needed because it needed for calculation. That is, I have to subtract the I square R loss. For the generator, it is needed because when you are calculating the generator loss for a particular load, we have separated the different losses, the windage, bearing friction loss, then brush friction loss, then the core loss. But the I square loss is just dependent on current. Those that is variable, so that has to be added. So the generator resistance has to also be calculated. When the resistance will be this voltmeter reading by the ammeter reading. Now, if you calculate, you will see that the resistance decreases gradually. That always happens for any machine with brushes. Now, for running condition, when the machine is running for quite a long time and temperature has increased, then in that case the brush contact that the brush resistance itself will decrease, because brush is made up of carbon, so it has a negative temperature coefficient. But for this case under the test condition, that is not only that is not very applicable, because we do not run the set quite some long to and that is that's why we perform the resistance measurement at the end, so that the temperature has risen so and the resistance has dropped. But while performing the experiment for different current, you can see that the resistance is also decreasing. That this drop is not due to the temperature rise. This what happens It is a contact between a carbon and the copper of the commutator. Now this contact can never be perfectly flat. There are basically point contacts between, because those two surfaces are not perfectly smooth, and it is not that perfectly flat contact between the brush and the commutator. So there are point contact between the brush and the commutator, and as the current increases, this point contacts goes on increasing number of points. So basically that's why the resistance goes on decreasing. Now normally for calculation, check there is no point of taking mean of these readings because this is variable actually. So we take the value corresponding to the normally it is customary to take the rated value, but the reading it is rated current is not available here. So take for the highest current rating for last one. Now for the report portion, from run 4, we have to find out the armature resistance of the motor and also for the generator. Then run 5, find the motor constant loss as P constant is equal to VAIA minus I square RA. Then from run 2, find the windage and bearing friction loss as VAIA minus I square RA minus P constant from here. For run 3, find brush friction loss as VAIA minus I square RA minus P constant minus this windage and bearing friction found here. Then from run 4, find the generator iron losses as VAIA minus I square RA minus P constant minus windage and bearing friction minus brush friction. Now all these curves has to be drawn. Now these curves all are increasing curve, that is the losses are increasing with this speed. We have to plot against the speed. So losses are increasing with speed, but this windage and bearing friction loss used in this are not perfectly linear. Windage and bearing friction loss is approximately square of the speed. It is a fan type of effect. So brush friction loss is exactly not linear, but almost linear. The slope is less for the brush friction loss. And so that we have to plot that windage bearing friction versus speed, brush friction loss versus speed. This iron loss also is not exactly linearly, because now we have to separate the two components, that is the eddy current and hysteresis loss from the iron loss. Now for that, plot the core loss versus speed, then take 2 points on the curve, N1 and N2. It is better to take 2 points in the more or less the middle portion of the curve. So your core loss, we have two components, that is eddy current and hysteresis. Now we know this eddy current loss is proportional to the frequency square and flux density square, and the hysteresis loss is proportional to the frequency into flux density to the power 1.3 to 1.2 to 1.3, which is Ten's constant. Now we have kept the voltage constant. So sorry, not the voltage, the field current constant. So that means your flux will be constant. So flux density is constant. So in that case, the eddy current loss become proportional to the frequency, which is proportional to the speed, and the hysteresis loss is proportional to the frequency, so it is proportional to the speed. So we can write the core loss is equal to some constant Ke into N1 square plus Kh into N1. So P core 1 for speed N1 is KE N1 square plus KH N1, and P core 2 is equal to KE N2 square plus KH into N2. Now we have got two equations, we know these losses, so we can find out these two constants. So finding out the constants, then we can calculate the hysteresis and eddy current loss separately, and we can get the curves. Now, if you plot from the here, you see we are plotting versus the speed. So this hysteresis loss will be linear because linearly proportional to the speed, but this is non-linear because it is proportional to square of the speed. Now, I will try to show some videos. Just wait. Just let me see whether I can get it or open it or not. Now this is connecting basically these are the two machines. This will operate as a motor. This is a generator. So this is the starter, 4-point starter. So he is basically connecting the DC shunt motor. It has got 4 terminals, 2 line terminals, one for armature and one for field. So this is from the armature terminal to the rheostat. Rheostat to the ammeter. So here these two are the ammeter terminal, these two are the series field, and these two are the shunt field terminals. We are not using the shunt field, so series field, so we are connecting as the shunt motor. These two are the rheostat, which is connected in the board, which will be used for the field stuff. So these two, this field and this armature has to be shorted, these two terminals. the voltmeter. He is connecting the voltmeter to the motor armature terminal. So these 3 meters in the motor circuit. This is a generator field connection. This is the rheostat. Rheostat has 3 points. These two are the fixed point. This is the variable point. This is the field ammeter. So this is the circuit. This is the rheostat. We have connected the potential divider and the ammeter. So the so voltmeter has to be connected. This field has to be taken to the field terminal of the generator from the board. So it is here. This F1 and F2. These are the field terminals. Here also we are connecting only the shunt field. We are not connecting the series field. So this is the voltmeter connected to the armature terminal of the generator. So both machines are connected as shunt machine. Say this is the brush holder. So he has taken out the brushes. So we take out the brushes and take that run without the brush. And this is a spring loaded. This is a copper band. We put the brush, then by spring pressure it will be there in contact. This is the copper brush. Sorry, the carbon brush. And this is how they uncouple. This is the coupling, so they uncouple. Now, under this condition, if you run, only the motor will rotate, not the generator. That is, both the machines are rotating separately. This is for some other experiment.